So Unit 1 is all about atomic structure. You're probably asking yourself, why are we studying atomic structure? Well, atomic structure provides us a lot of information. It provides us the what's positively charged, what's negatively charged. It also talks about, we also learn about the law of charges, about like charges repelling and opposite charges attracting. It can explain a lot of our electrical phenomena. It also defines, atomic structure also defines the different types of material that we'll be working with. Well, as electrical workers, we deal with conductors, semiconductors, and insulators. So knowing the atomic structure, we can define these classes of materials. The other nice thing about atomic structure, it actually tells us or defines what's moving in the electric circuit. Our objectives are to list the three principal parts of the atom, as well as identify where those parts of the atom, where they are inside the atom, as well as the charges on those parts of the atom. Next, we need to state the law of charges. Not only state it, but understand it and be able to apply it, because we can apply this to many different types of electrical phenomena. We need to also discuss the difference between centrifugal force and centripetal forces. These are forces that are acting within the atom. We need to discuss the different classes of materials. We need to talk about the differences between conductors, the differences between semiconductors, and the differences between insulators. So we all know that electricity is pretty important. Imagine spending a day without electricity. You wouldn't be able to wake up. You wouldn't be able to cook your eggs. You wouldn't be able to watch TV. You wouldn't be able to charge your cell phone. You wouldn't be able to do a lot of things. So again, electricity is a driving force that provides most of the power in the industrialized world. We rely heavily on it. Now, there are two types of electric sources. We have what's called a DC source, which is known as a direct current source. It's unidirectional. That means that once we connect that voltage supply to our circuit, current will only be in one direction through the circuit. So here, it's a cross section of my wire, shows the direction of the current for a DC circuit, only one direction. When we're talking about AC, we're talking about alternating current. Alternating current is referred to as bidirectional. It means that it travels in two directions. During one part of the cycle, the first half of the cycle, the current will be in one direction. On the second half of the cycle, the current will be back in the opposite direction. So this is the difference between AC and a DC voltage source. So let's talk a little bit about the history of electricity. Now, don't be concerned. This is a Principle of Electricity's class. We are not studying history, and you will not be tested on any of these dates. But sometimes it's interesting just to go back and look at the progression. So 2,500 years ago, the Greeks discovered electricity. They just determined that this stone that was called amber could be charged. So that's actually where the term electron came from, way back then. Early 1600s, William Gilbert discovered that some materials could be charged while other materials couldn't be charged. He called them electrics for the materials that could be charged, and he called them non-electrics for materials that could not hold charge. So about 300 years ago, Charles Dufay experimented with different types of charge. He would charge up glass rods. He didn't know what the actual charges are. He actually gave them a list, put them on lists, list A and list B. And he found out that he could put some charges on the glass rod and it would attract other types of charges and it would repel other ones. So this is the early beginnings of where we started to investigate and determine the law of charges. So here is an example of Dufay's two lists. He had identified two types of charges. He wasn't sure what to call them, but he put all the one type of charge onto list A, all the second type of charge onto list B. For example, he found that if he took a glass rod and he rubbed it with silk, or he took a glass rod and he rubbed it with wool or cotton, it produced the same type of charge on the glass rod. However, if he took for example, a hard piece of rubber and he rubbed wool on it, it was definitely a different type of charge. But it was the same charge that if we took a block of sulfur and we rubbed it with a wool or fur, that it would be the same charge as hard rubber that was rubbed with wool. So what Dufay did is identify these two types of charges, and he put them on lists. So what we see in these diagrams here are the two types of charges that Dufay identified. The charges in list A and the charges in list B. They're two separate charges, and what these diagrams show is how these two charges interact. What Dufay found is that if I had a charge from list A and I had a charge from list B, what I would end up with would be an attraction between these two charges. He also found that if he took two of those objects charged with the same charge, for example, list A and another one charged with list A, what he found is that there were actual repulsion forces. Same thing if I charged up objects with one object with a list B charge and another object with a list B charge, we would find that there was actually repulsion forces where they would push away from each other. So from here, we can clearly define the law of charges. We can say that from looking at the top diagram that opposite charges attract. From looking at the two lower diagrams, we can see that like charges repel. So that is the law of charges. So we need to start talking about atomic structure, primarily the atom. The atom is the building block of the universe. Primarily, atoms combine together into what are called molecules that make up matter. And basically, atoms are made up of what are referred to as their elements. They are a substance that can't be divided into a simpler substance without ruining the integrity of the actual substance. So we're going to talk about the principal parts of an atom today. We're going to talk about the proton. The proton is a positive charge. It's a particle that's positively charged, and it's located inside the nucleus of the actual atom. So here's our diagram of the atom. We have electrons. Electrons are negatively charged. They are not within this nucleus, the center nucleus of the atom. They are orbiting outside the nucleus in what are called orbital shells or orbital rings. Electrons have negative charge. Neutrons have no charge. Neutrons, they're neutral. They are located inside the nucleus of the atom. So we're talking about the atom. We're really talking about the nucleus, what's contained in the nucleus, and what's contained in the orbital rings or the orbital shells around the nucleus. So if we're looking at our diagram, we know that the protons and the neutrons exist in the nucleus, and the electrons are what are orbiting around the nucleus. Here's an example of water. Water is a molecule. It's made up of two parts of hydrogen and one part of oxygen. Water can exist in three states. It can exist as a solid. We know it as ice. It can exist at water as a liquid. We use this every time we take a drink from the drinking fountain. Also, water can exist in the state of gas, which is also known as steam. So here's an example of matter. Matter existing in three different states. A solid, a gas, and a liquid. And you can see here, looking from the chemical equation here, that water is a molecule because it's made up of its elements. It has 2 parts of hydrogen, that's what the 2 stands for, and it has 1 part of oxygen. We call it H2O. So let's take a closer look at some atoms. We have a table of elements that's located in your standard textbook of electricity on page 33. So turn to that now and let's look at figure 1-4. When you're looking at the figure 1-4, you'll see a table. In the table, you'll see columns. The first column is the atomic number. The atomic number of each atom, it tells you how many protons are located in the nucleus. The next column tells us the name of the atom. The third column is the valence electron. When we're talking about the valence electron, we're talking about the electron that exists in the most outer orbit. So for example, if we have an atom that has a nucleus, and it can have multiple shells or multiple orbits where there are electrons that exist in these orbits. When we're talking about the valence shell, or the valence ring, the valence electrons, they're located in the most outer ring, this most outer orbit. Those are the ones that we're concerned with as for studying for this class, the valence shell electrons. Next, when you look at the table in figure 1-4, you'll also see that the last column in the table is the symbol. This is the chemical symbol that we use to represent. So for example, we look at the first row in the table, we see that it has we're looking at hydrogen. Hydrogen has the atomic number of 1. That means that it has 1 proton in the nucleus. It has, if you look further, you'll see that it has 1 valence shell electron. It is symbolized by H. We saw that before in our example of H2O. Hydrogen. Hydrogen uses a capital H for the symbol. So we're going to use this table because this table will help us to identify different types of materials. So for example, if you scroll down to, or if you look down to number 29, 29 is copper. Copper has 1 valence shell electron. Copper's number, or symbol, is capital C, lowercase u. So it has 1 valence shell electron. Well, we know that copper is primarily the material that's used in wires. It's used as our conductor, and it has a valence shell of 1. Another type of conductor that you should be familiar with is aluminum. So when we look at aluminum, aluminum is number 13 on the list. So it has 13 protons in the nucleus, but you'll see that it has 3 valence shell electrons. So when we look at copper and we look at aluminum, even though they're both conductors, copper is a better conductor, and you want to make a note of that it has 1 valence shell electron. So let's look at some other types of conductors that you may be familiar with. For example, let's take a look at silver. Silver is number, I always lose it on the table here, where is it? Silver is 47. So atomic number 47 is silver. It has 1 valence shell electron. Silver is a very good conductor also. You look at the symbol for silver, it's a capital A, lower letter G. Can you think of another conductor? Let's think about gold, 79. You look at 79 gold, it has 1 valence shell electron. Its symbol is A, capital A, lowercase u. So when looking at good conductors, we see that good conductors have a lower number of electrons in the valence shell. What we have here is Bohr's model for the atom. Bohr's model for the atom basically consists of a nucleus and orbital shells. This is the helium atom. The helium atom is an atom that contains two protons in the nucleus. So right here is the nucleus of the atom. And in there we can see that there are two protons, and we know those protons are positively charged. We can also see in this diagram that there are two neutrons. Neutrons are neutral. They have no charge. So the question most people ask is, why are there neutrons? Well, what do the neutrons give us? What the neutrons give us is mass. They add mass to the actual atom. So that's what we find in the nucleus. We find neutrons and we find protons, and they're located in the center of the atom. Out in the orbital shells, we have the electrons. Electrons are negatively charged. So here's an example of an electron in the orbit with another electron in orbit over here. There's only one orbital shell. It is the most outer orbital shell, so it's the valence ring, and we know that there's two electrons that exist within this ring. So this is Bohr's model. This is the model that we're going to use to identify the different parts of the atom and where they are located. So in the diagrams that we see